Again, so we're talking on the physical properties of alcohols and ethers. And the physical properties of alcohols and ethers could only be derived from its structure. So we'll look at later on we will scrutinize on the structure of alcohols and ethers and why would its properties be different. Okay, so the reason why we're having these alcohols and ethers in the same chapter is that of course there's an oxygen bonded to carbon, and the only uh, group of atoms being different in alcohols and ethers is the alkyl group that is bonded to your O in ethers, while in alcohols you have your hydrogen bonded to your O. Okay, so as I mentioned earlier, your ethers have some comparable boiling points, so that of hydrocarbons containing similar molecular weight. But if you try to compare ethers and alcohols, alcohols actually have a higher boiling points than comparable ethers or hydrocarbons. Okay, for instance, you have your butyl alcohol. Can you imagine in the structure of butyl alcohol, you have your CH3, CH2, CH2, 4 carbons with an OH, no? And the molecular weight is 74, and we try to compare that with diethyl ether, 4 carbons also, but an ether O, CH3, CH2O, CH2, CH3. You have that, no? The boiling point for ether is 34.6, but that of alcohol is 170. It's very large. So how do you think can we account for a high boiling point of alcohols relative to ether? Katugon ako. Anyone? Aisa. Or do you think alcohol would have a higher boiling point than that of ether? Aisa? Donna? Anyone? Tom Jerry?
It's okay to question, ma'am.
Why do you think that alcohol would have a higher boiling point than that of ether, having comparable molecular weight? Like in this case, butyl alcohol, the boiling point is 117, while that of ether, you have only 34.6, very volatile. Why do you think so?
Naman siya yung hydrogen bond, ma'am.
Kinsa man.
Sa alcohol.
Okay, so alcohol would exhibit hydrogen bond as its intermolecular force of interaction between the molecules. So that of ether, you only use the dipolar interaction, right? So we'll look at the structure of our ethers and alcohols. Your alcohols, for example, your CH3OH here, we look at the individual bond polarity, your O, the electronegative atom, no, would exhibit a partial negative charge, and your hydrogen will exhibit the partial positive charge. So when it is adjacent to another molecule of your alcohol, no, the partial negative charge of your oxygen, okay, will be attracted to the partial positive charge hydrogen here, the other molecule, and that will be the basis for the hydrogen bond formation. And if, for instance, the second molecule here, having an oxygen bearing the partial negative charge, it also exhibit a hydrogen bond formation in another molecule of hydrogen of the alcohol, having your hydrogen that has partial positive charge, partial negative and partial positive, that you have your hydrogen bond formation. We also have here. Okay, and as we've learned that hydrogen bond between molecules is actually very strong. And this is the basis why you have your hydrogen, why you have your alcohols would have a high boiling point. In diethyl, however, they don't form hydrogen bond with compounds such as water. And because of that, no, you expect the only force of interaction that exists in ethers are the dipole interaction, dipole interaction. And we've learned that the hydrogen bond is much stronger than the dipole interactions. You expect your alcohols to have stronger boiling point. In fact, if you look at on the boiling point of our alcohols, okay, the boiling point is very high. So for instance, beta alcohol, you have 117 here. They should have shown the molecular weight anyway. So you have your beta alcohol here, 117. And si diethyl kaganina, ang liingan, diethyl ether with comparable weights sa imong beta alcohol is very, very low, 34.6. The melting point also, it's very, very low as compared to the melting point of the alcohol. Okay. And a similar way, as you increase in the number of carbons of your alcohols, you expect also that the boiling point increases, like here. So as a butyl alcohol, you have your methanol, ethanol, propyl alcohol. It's propyl alcohol, and the boiling point increases. You have here. So 1 carbon, 2 carbon, 3 carbon here. And branching actually decreases on the boiling points. You can see between the propyl alcohol, you have secondary alcohol here and the propyl alcohol. Okay, it's because of the inductive effect, electron withdrawing inductive effect. Electron donating inductive effect that will be exhibited on this H2 here on carbons. It will, as compared here, so you expect your oxygen to be electronegative, partial electronegatively charged in the presence of 2 alkyl groups, touch your carbon, inducing on the oxygen here to be partial negative charge. So you expect this one would have a low boiling point. Okay, what else? So isobutyl alcohol, secondary. You can see on the butyl alcohol, you have the terminal one. It's compared if there is branching here, it's much lower. The boiling point is much lower here, 108. And if you have a secondary alcohol, it's much lower than the primary. Okay. And then more branching here, you have a lower starting point, you can see. And the higher the greater number of OH, you have your dione triol, you can expect the boiling point to also be greater than naalay isa ka OH to your compound. Okay, and of course, expect the solubility decrease as the number of carbon decreases. So at a very few number of carbons, expect the solubility in water to be infinite, but increase in the number of carbons, solubility decreases. Okay, what else? For ethers, of course, you didn't see any structure. You just see in the structure, the oxygen to bear partial negative charge, while you have the alkyl groups to be polarized. And you have the dipole-dipole interactions. The diethyl ether and 1-butanol have the same solubility in water, approximately 8 grams per 100 ml from temperature contained. The contrast, so there is no point over there is an electronegative atom where there is a point where you can see the molecule to be polar. Expect your pentane to be virtually insoluble in water. And for alcohols, expect them to be completely soluble in water. And alcohol, as I mentioned, the solubility of alcohols in water Gradually decreases, the hydrocarbon portion of molecules lengthens, right? So the stability decreases as increase on the molecular weight. Why is that? Of course, the reason is that the increase in the number of carbons, the increase on the hydrophobic end of your molecule, and therefore the solubility also decreases. Okay, so I'd like to go on the reactions, no, kay katugon ko ani nga mga istorya. So there are important alcohols and ethers. Okay, you have your methanol, and you have this way of preparing. Methanol is we can start with carbon monoxide and hydrogen gas. This is the industrial way of preparing your or useful methanol. So what do they usually use? Like for example, methanol. Now we don't use atong gamit usually, but methanol is highly toxic and can actually induce poisoning by insulation, and especially if you have a prolonged exposure to that. And what is the use for methanol? So most methanol, consider your methanol to be a wood alcohol. You can use your methanol as your solvent. And for the production of this, it is prepared by catalytic hydrogenation of carbon hydroxide at a very high temperature, and there is a catalyst, zinc oxide and chromium oxide at a very high pressure. Imagine, no, it's a very, very high temperature and a very high pressure reaction using the carbon monoxide. And this is the industrial process of preparing your methanol. And methanol also is also called the wood alcohol. And this one is very toxic. We don't ingest methanol. That's why for some other people would have a poison if they drink some alcoholic drinks that would contain methanol. Okay, so this is a way of preparing your methanol industrially for the use of methanol in industrial use also and laboratory use. For ethanol, another important alcohol, you have your ethanol. We can make ethanol by fermentation of our carbohydrates and simple sugars. And ethanol also is the alcohol that we can find in alcoholic beverages. And in fact, was it yesterday or Wednesday, you were able to extract your ethanol via distillation last Wednesday in your laboratory. And yes, you can find that one in alcoholic beverages. And the synthesis of ethanol in the form of wine, you can synthesize your ethanol in the form of wine by fermentation of sugars. So I think this would also be one of the activity probably that will give you. Maybe you can prepare some alcohol from food sources. You can choose a particular food that you would like to start with. You can prepare your wine. The usual fruit that's being used for the preparation of wine actually are the grapes, grape vines, but you can also prepare actually your wine from food sources. So I think I'm gonna upload for that would be your also next activity, preparing your wine, for this chapter. You can have your source of alcohol. Of course, the alcohol content is just around, the highest one would be around 14% and range from 14 to 9%. But the sweet one is just around 4.5%. For it's very different. Alcoholic drinks very different for katong mga gins and rum and others, because they actually use distillation process where they can increase the alcohol content from their alcoholic beverages. So what we're talking here is just wines can be prepared from a variety of fruit sources. So alcohol also is a common name for them is the grain alcohol. Usually can produce or ethanol via the fermentation process, and that's what you're gonna do. You prepare your wine from alcohol sources. So Samantalang June, before the semester ends, no, I think I'm gonna ask you to, karon pa lang, I'd like you to think na your source to prepare your wine for your laboratory. Okay, and of course to do that you will use this and can find from some online sources how to prepare your wine. And alternately, for you to prepare your wine, can also add just to give a different taste. Now, if you notice some woods nga that would have a lot of tannins and some other medicinal benefits, you can also include that while you do fermentation actually just to add another flavor to your wine. And in fact, that's the reason why some of the producers of wine from which countries they always actually have to produce their wine from kanang mga barrels is made up of woods because the tannins, the woods have some tannins that gives a different flavor. Also the source of the fruit or the grape vine. So much for that. You can also prepare your 1,2,3 alcohol from our ethane. And this is the industrial way of preparing our alcohol. Can have this is just an addition reaction in your water and the acid. So most ethanol for industrial process is produced by the acid catalyzation of ethane. Fermentation alone does not produce beverages with an alcohol content greater than 12 to 15% because the enzymes of the yeast are deactivated at a higher concentration. And it is for this reason that when we prepare alcohols via the fermentation process, particularly for wines, they only produce an alcohol, a wine having an alcohol content up to 14 to 15. No, again, here it said because the enzymes of the yeast are deactivated at a higher concentration of the alcohol. And this is the one I have mentioned. Nakatong other types of beverages of alcoholic beverages having a higher alcohol content. For example, mga bars, mga gins, rums, the aqueous solution has to be distilled, no, so that what is being added to your alcoholic drinks will have a higher percent of alcohol. But of course, masala na siya. Okay, so ethanol, but for industrial purposes, now this one, of course, you don't use this one for ingestion, this kind of process. You'd rather use have that having the fermentation. So there is this industrial grade for food, and there is an industrial grade also that is for chemical industry. So you notice if you drink alcohol, ethanol actually is a hypnotic, it's a sleep producer. So I don't know, I didn't drink alcohol, but I'm just sleepy for now. I think I did coffee. So ethanol is a hypnotic sleep producer. It depresses activity in the upper brain, even though it gives the illusion of being a stimulant. Ethanol also is toxic, but it's much less toxic than methanol. So be careful when you are drinking. If you drink, no, do not be addicted to alcohol, not to ethanol. And when I was in France, no, people actually are very much into wine. Every house there would actually they have a variety of wines, no, that they would serve to their visitors. And the alcohol content for wines just actually just around 15%. It wouldn't give you really a feeling of an habitual, no, just to induce a sleep producer and some kind of a stimulant. Although it gives an illusion of being a stimulant, no, somehow mura kag when you have a lot of alcohol in your system, in your body, but be careful because it also has a depressing activity. It somehow stimulates to produce another hormone in your body where you feel like also depressed. Okay, so that's it. for alcohols, and I would appreciate if you will really prepare your some kind of wine or to your ethanol. So ethanol can also serve as a biofuel. In fact, if you look at some of the kind of gas stations, no, they have added ethanol as a biofuel. And ethanol is said to be a renewable energy source. It can be made through fermentation. Yes, of course, can have that one. So it's used as a replacement for gasoline. Ethanol has a lower energy content, however, by about 34% per unit volume. This and other factors such as cost and energy required to produce agricultural feedstock. So the only thing that with ethanol, no, as a source of biofuel, no, because the costs in energy required to produce agricultural feedstock, especially corn, have created doubts about the wisdom of ethanol-based programs for renewable energy source. Actually, it's very also expensive to use ethanol as our energy source. The production of ethanol from corn is six times less efficient than producing it from sugar cane. So it becomes actually a competition, no, with other source to produce competition, food production competition, no, as our source for if you're trying to find energy resource using this one. And you have your world food shortages may also result. For example, they are producing ethanol from corn or they are producing ethanol from sugarcane. So it can also limit or compete for food production, for food resource. So that's why some others also question on the use of ethanol as a biofuel. But even though you still see a lot of manufacturers uses ethanol or add ethanol to the gasoline. Okay, so I think you can just read on this. So you have here ethylene, propylene glycols, your properties. You have your diols here, an important ethanol. You have your ethylene, propylene glycols. Miscible with water, of course, they are used as anti-automobile, antifreeze. What is the structure? I'll let you put down. Anyway, makita niyo, this is the structure of ethylene glycol. You have your OH, H2, expect this one to have a higher boiling point than that of an ethanol, no, because there is two OH here. There is a greater hydrogen bond formation between molecules. And because of that, no, there is a greater force of interaction with water. And it made ethylene glycol a good automobile antifreeze. Now the melting point is very, very low. So compared to just ethanol and water. So in the presence of, for example, a very extreme weather condition during winter times, now this ethylene glycol added to your engine, no, it will actually promote antifreeze. So dili mo gahi because of this, because it is a very, very low melting point. Okay, so we also can use propane glycol. Another one important product, you have your diethyl ether. Diethyl ether is a very low boiling, highly flammable liquid. Care should also be taken when diethyl ether is used in the laboratory. Because open flames or sparks and lights such as can cause explosive combustions of mixtures of diethyl and air. So diethyl ether, whenever you're using the lab, no, even other ethers, have to be careful because it can be flammable. When you're using open flame or when there's a flame around, make sure that you cover your ether so that it wouldn't catch fire. No, it's very flammable. So most ethers react with oxygen with a radical process called auto-oxidation. So we have already discussed the similar process they have shown earlier. Now you have your hydrogen. You have your hydrogen. You have your diradical oxygen here. In the presence of light, your O double bond O, the pi bond can be broken. And you have your radical. Each of the oxygen in the oxygen will have a dot. There's an unpaired electron there. And once you have your ether, the oxygen would form a bond with the hydrogen from your ether. And you get your hydroperoxide here. And then you have a radical ether, radical here. But your radical is in carbon. So once you produce your radical, it reacts with another oxygen. And again, you get your peroxide here. So how do you do that? You'll have your O, you have your double bond. Remember, your oxygen is O, double bond O, with oxygen having 2 unshared electrons. The 2,4 from the double bond and 6,8 from the unshared electrons. Okay, so when with the presence of the radical, it forms a bond with oxygen via homolytic bond formation. So pag isa lang ka-electron yung gamiton, one of the electrons of the pi bond will go sa inyong oxygen. So you have here, form a bond here by homolytic bond formation with oxygen, and there will be a single bond and a dot on oxygen. Once you do that one, you get another mole of your ether, you get your hydroperoxide. Your hydroperoxide, get here your hydroperoxide. This is also a hydroperoxide. Hydroperoxide, where you have your OR, carbon OOH here. Okay, and then you have another radical, and so it is a continuous process where once you have here your hydroperoxide will react with another ether, radical ether. What you actually get is peroxide, hydroperoxide kani will form here, this one, but your OO dot kani will form with your carbon. This one is very, very unstable. Once you form this kind of hydroperoxide, it will cause to explode. So you have to be very careful when you are using diethyl ether in the lab. So okay, I wanted to proceed now with the reactions. The hydroperoxide peroxides often accumulating ethers have been stored for months or longer in contact with air, are dangerously explosive. So once you are storing your ethers now in the lab, and in the presence of heat and light, may be able to produce hydroperoxides and peroxides. So you have to be careful, which often occurs in ethers that have been stored for months or longer in contact. The air in top of the bottle is enough or dangerously explosive. So for example, if you will be in the laboratory and you are storing with you the diethyl ether, you have to be careful when you're trying to shake your ether, because even the air on top of the bottle, inside the bottle, no, can react with your ether and will form hydroperoxides and peroxide, which can be very explosive, no? And they often detonate without warning when ether solutions are distilled to near dryness. That's why you have to be very careful. Since ethers are used frequently in extractions, one should take care to test and decompose any peroxide present in the ether before distillation is carried out. When you will be doing your thesis and if you're handling with ethers, so you have to be very careful. So also ether is one time used as surgical anesthetic, although nowadays they use usually the haloethanes. Ethanes with halogens added to it now, because of course the storage of that is very dangerous for ethers, and unlike the diethyl ether, which is flammable, and this is very dangerous once it's stored in a prolonged manner. Now the haloethane is not flammable, so that for medical practitioners, you'd rather use the haloethanes in your ethers. And you can just read on this cholesterol and heart disease. Maybe next time I'm gonna ask you, do you have learned anything from this? So we'll go before we end. So we'll just review on how we prepare our alcohols from our alkene. In chapter 8, we've learned about how the reactions of alkenes to form alcohols. So we'll do those kind of reactions to prepare our alcohols. No? And so we have studied the acid catalyzation of alkenes. You have the oxymercuration, demercuration process, and you have also the hydroboration oxidation process. And all this kind of reactions actually will yield alcohols, no, from alkenes. So we'll summarize this. And before we end, the next meeting we'll be discussing on the reactions of our alcohol. So here is a part to produce our alcohols from alkene. The first one, and this is just a review, is the acid catalyzation of alkenes. You have your alkene, you have your acid, and of course in here, this becomes your acid, this becomes your nucleophile, your base. No? So we will use on the electrons on the pi bond to form a bond with hydrogen, okay, and the electrons in the acid from HA will go to the conjugate base here. So you have your C hydrogen bond, and one of the carbons will become a carbonate ion, and another water molecule. We will actually produce our protonated alcohol here. So you use the electrons from the alcohol to form a bond here. You get your O. HH here, where this is a protonated alcohol, and another mole of your conjugate base will remove the proton from alcohol and that's your alcohol. So there are advantages of this reaction is reversible, and we have already learned that the mechanism for this reaction will always produce our carbonate ion, and ways to stabilize our carbonate ion lead to a faster reaction. And here in the reaction, the standard reaction actually follows the Markovnikov rule. So the Markovnikov rule, the carbon that contains a higher number of hydrogen will have the hydrogen as will have the carbon added with the hydrogen from your acid. And the fewer number of hydrogen to that carbon, the ion will also be added. Also, you have the rich gets returned, the poor gets poured. In the oxymercuration, demercuration process, there are two steps to produce this one. So here you actually first prepare your OH. One of the carbon atoms, the double one, will have the OH and the other will have the mercury acetate. Okay, and then further removal of this, the hydrolyzed H3OAC will have be replaced with hydrogen. So this kind of reaction, you just have to be careful because mercury compounds are hazardous. So if you carry out this reaction, you should have to familiarize yourselves how to dispose this one and how you protect yourselves from handling mercury. So once you have your H2AEC, you can actually reduce this one, the mercury, which the mercury has the H2 plus. So you can reduce this one so that you get your hydrogen here replaced and use a reducing agent, sodium borohydride, in the presence of a hydroxide. So there are two steps for this oxymercuration process to get your alcohol. First one is the mercury oxymercuration in the presence of H2OAC and H2O. So you have to always remember other agents need to be used. And then second step is the demercuration process where we use a reducing agents such as sodium borohydride in the presence of base OH. So the only thing here is that in here, you notice here the 8HgO plus this the net addition of hydrogen OH takes place with Markovnikov ridge selectivity here. So if you have your alkene here, the end product once you have here is the mercury will add to the carbon containing a higher number of hydrogen, the OH will be added to the carbon containing a fewer number of hydrogen, and the net product will have your following the Markovnikov reaction, and your carbon containing a higher number of hydrogen will have your hydrogen added to it. In the first step, it is the mercury acetate being added to the carbon containing a higher number of hydrogen before you get your final product here. So you just have to note that. And the overall reaction, however, is that alkene hydration is not very selective, because even though the oxymercuration step occurs with anti-addition, the demercuration step is not very selective. Radicals are thought to be involved, and hence a mixture of syn and anti-products would result. So once you have here, like this one, this is you will have the syn addition. and you have an anti-addition of your mercury involved. Another kind of reaction is the hydroboration oxidation process. No? Here you have the anti-mechanical addition. You have your BH3 added here. And you have your hydrogen being replaced with boron. The mechanism for this you can review on the chapter 8. And then you have another, this is the hydroboration step, the first one, after you get your boron with an alkyl group attached to it, you can substitute all this R with your alkene here. And then the second step is the oxidation process. You have your OH. Boron will be replaced with an OH using a hydrogen peroxide in the presence of a base. Okay, so that's it. And that's our session for today. Now we'll upload on for you something to practice on. Before we end, we can think of, as a note, this hydroboration oxidation process follows the anti-Markovnikov rule. You know, like, for example, here you have a double bond. Here contains a higher number of carbon. For a normal Markovnikov addition, this should get the hydrogen and this one should get the OH. No, but in the hydroboration oxidation process, it follows the anti-Markovnikov's rule, wherein the hydrogen is being added here and the OH is being added here. Okay, so if you want to go through back, follow again on the mechanism of this kind of reactions, or you have to perceive what kind of product will be produced. And you have to familiarize yourself with the agents being used for each particular kind of reaction. So what conditions do you use for each reaction? If you have, for example, an alkene here and an OH, no H is the first one. So here you have your CH2 and here you have no hydrogen. And you will have your hydrogen added here and the OH added here for this to get your alcohol. And the other one is your hydrogen added here and the OH is added here. So letter B is an anti-Markovnikov rule, or follows the anti-Markovnikov rule, and letter A follows the Markovnikov rule. What conditions would you use for each reaction? Tom Jerry, what do you think will be your agent if you want to prepare this kind of alcohol from this alkyl, letter A? Kalimut naman sa inyong alkene. Hopefully, I can bring you the results for your midterm exam soon. Nakalimut na mo. Actually, you can just even use the HA, acid, the presence of a catalyst. It follows the Markovnikov addition. Like, for example, HBr. Okay, you can have your hydrogen, HBr. You can have your H2O and the presence of an acid. Okay, H2SO4 and water, of course. So you have your H added here and you have your OH added here. Or you can use your oxymercuration demercuration process, wherein you follow the Markovnikov's rule addition, and letter B, you can use the hydroboration you have the hydroboration and dehydroboration process here. Okay, so you can use your BH3, your boron compound in the presence of THF. The second step will be the removal of your boron using the peroxide in the presence of a base. But the first one, as I mentioned, you can always use your ketone acid and water, like H2SO4 is your catalyst, and water. You can add follow some Markovnikov addition, or you can use the other agent